button. So we'll start off now with the recording. So anyway, today we're going to be talking on that area of how do we actually measure and record the signals, and then just briefly, and then go into actually processing it. So as I was mentioning just before I hit the record button, cones, we inject gel into them, different set locations around the head. Um, so we kind of divide your head up to, it's kind of hard for me to show here. Um, but if you can kind of imagine, right, I've got my prefrontal, my frontal, right between my ears. You've got, in the middle top of the head, you've got central, parietal, kind of on the back upper region, then the occipital on the far back, and then the temporal lobes along the side. So when you see a lot of the recording ones, they'll usually show like an oval with two ears on the side and a little triangle for the nose. And then, they'll have labeled, usually starting running down the center and then between the ears, you will have, kind of that central area that's labeled off. Um, the middle, right down the head, is the zero line. Usually, we don't put um, the circle for zero. We use the letter Z for zero, and that's because you've got the occipital lobe in the back, and it looks too darn similar. So we use Z for zero, so we can use O for occipital. Um, and then you do even on the right the numbers and odd on the left side, 3 and 2. So that's the basic way that um, most of the nodes tend to be labeled, but that's not a guaranteed. So there are going to be some special ones that will go in. So that's going to be one of our big issues is how did the person label their channels? They're going in. Um, these are, electrical signals, right? Electroencephalography, EEG. It basically, once you've got a good connection to the head, which, means bypassing hair and all that kind of stuff, um, and you're recording them, it, it's basically going to be just like what we did before, just a little bit stronger amplification. So that's going to be kind of a big area. You just slightly tweak up. You will get noise, but there's no way to avoid noise on these channels. We're going to try to find ways to characterize the worst of the noise. Um, but I'd rather have noise in my signal and than not have a signal. So that's, when we process the data, that's going to be an important thing. There's a certain amount of noise you're going to have to realize you're just not going to be able to get rid of. Um, let's see. Some other ones that are kind of worth noting. You've um, probably heard of EEGs before. You might have heard of MEGs, the magnetoencephalographies. Um, so I can measure the electrical like we've done before. We can also measure the magnetic field that's associated. You can get very, very sensitive magnets, place them around. So those are called MEGs. It's just another way of reading them. We did just finish pulse oximetry a little bit ago, and I mentioned, near infrared spectroscopy. When we do near infrared spectroscopy across the entire head to try to determine, similar to EEGs, how brain function works and things of that sort, we call it functional near infrared spectroscopy, or FNIRS. So when you see a similar type of an array, but we're using optical measurements, then you'll have the FNIRS moniker that goes on. That's actually where I've done more of my work. Um, FNIRS works slightly differently. You're measuring basically blood flows and oxygenation, um, but there's a basic response within the body when your brain starts having activity. It requires more blood flow, and so the blood flow and oxygenation tends to follow pretty closely, but a slight lag behind the actual activity. So you can also use blood flow and the NIRS type measurements we just did to monitor brain activity. Um, my particular interest in this is actually from working with some doctors whose major concern is protecting the brain during surgery. So they want to know how the brain is behaving, and that's as surgery is going on and trying to find out what's happening there. So that gives you kind of the basic rundown of some alternative ways of measuring them. So we've got EEG, MEG, FNIRS. I guess for completeness, we can mention functional MRIs. So MRIs are used to measure spins. Um, to kind of make the, if you're really interested in it, take the biomedical imaging course that I teach. And we actually go in and process and make you actually make you measure your own MRI image, stuff like that. Um, but when you actually take these MRI images, you're measuring basically how easy it is to spin. If you've got an odd number of fundamental particles inside your nucleus, you're going to have a spin moment, and you can spin them. One of the most common one, therefore, because there's water is what makes up most of you is hydrogen. Hydrogen has a spin moment, so we can spin these. And if we find, so most of what you're measuring is hydrogen spin in an MRI. Um, but we can also look at how these ones are flowing and uptake as a result of brain imaging. So if we image an area and we kind of keep repeating these images to take a look at flows and that, we can actually get a functional measure of these. So we can actually watch the individual pattern as the brain changes during thoughts. And this type of a study for as the brain is functioning doing a task becomes a brain function study and hence an fMRI. The neat thing about fMRIs is it will allow you to measure everywhere inside simultaneously. Um, you're actually measuring one frequency at a time when you're doing that, but um, that's actually somewhat helpful. Um, you're technically measuring frequency ranges, but everywhere, and then they have to kind of reverse it. So they technically you're reading the functional space, and then you do an inverse Fourier transform. They don't call it function space; they call it K space. I don't want to go too far into this, but um, because we are interested, this is kind of a neat function. I can, since I'm measuring frequency, I can actually concentrate on a particular band if I want to. So these are the kind of different methods. We're going to concentrate on EEGs, where we've taken a bunch of measurements on the outside. To be able to map them to regions of the brain so we can determine what does what, we're going to need to then take those signals. We need to know their locations, and we're going to have to then, um, extract out from these signals, say, hey, look, this pattern happens on all these areas. Where did it come from? This is essentially the same thing as we talked about when we discussed a week ago the videos basically where we talked about blind deconvolution. So hopefully you've watched the stuff on blind deconvolution. Um, we're basically going to, blind deconvolution. One of the solutions is ICA. And the classic problem is called the cocktail party problem. You got people talking inside a party and you've got recording devices and you want to separate out each person's thing. Now, your brain is the party. People, each section of your brain that does different functions are different speakers. They each have a kind of task or an interest that they're in. The electrodes all around the outside, right, going from the prefrontal to the occipital, around the temporal, stuff like that. Right, we've got all these microphones on the outside. We want to find out what's happening inside. We can measure what the surface activity is. We have to know where those electrodes are. That's why we have these regions. We kind of designate the locations fairly precisely so that we can now map it accurately back to your brain. That's the basic thrust of trying to get the measurements and the locations very accurate, is to be able to map them not only just to the surface areas, although that's going to be our first part, but technically speaking, you can do this in 3D, so we can resolve things further in. What you discover when you do this is we basically think on the outside of our brain, kind of generalities, but in your gray matter tends to do the thinking, and the white matter inside tends to be kind of like the interconnection network. Gross simplification, but gets the basic idea across. Um, So, we're going to do a lot of ones where we're just going to show 2D maps of the surface of the brain because by and large, that's often what we're interested in. But you could technically use these exact techniques, and EEG Lab has the ability to do 3D plots. All right. So I'm going to share my screen here in a second. We'll go through MATLAB. But does everybody feel comfortable with the basic idea, how this connects to the other ones, how the measurements go? Because the rest of today's thing is really just going to be doing the processing. I'll give everybody a sec to think. All right. Well, hearing nothing, I'm going to presume that we're all very happy and that you have your caffeine and you just haven't fallen asleep on me. Um, I see a yes
Sorry.
from Patrick. So, oh, no problem. So one of the things I've noticed, I imagine all of you have too, right? We're all kind of stuck inside right now with, the whole COVID thing going on. And, so you're probably watching a lot of videos and that. It's really easy to kind of drift inside these. Um, so start thinking about this actually as, in a bioengineer, right? So, you know, remember, as you're kind of sitting there, we often have this basic curve. When you looked on it, under most of the cases, except when I was like really actively involved in something, I tended to have this kind of like 1/x curve dropping off, or exponential kind of drop off as it goes to higher frequencies. That's very characteristic of kind of like a passive brain type of thing. Um, so if you're only just listening to me, you're going to come along, you'll get, you know, a very strong theta waves, you'll get a little bit of alpha wave activity, but the betas and the gammas will kind of drop off because you're just following me. Your brain doesn't have to be particularly active when you're just listening. Um, so it's very easy during that thing to kind of get lulled in, and then your brain just kind of goes off where it wants to go, and that's kind of characteristic of theta wave activity. So every now and then it's good to kind of jar that up. You can do that yourself by asking yourself that question. How does this connect? Where does this work here? Right? I can also try to stimulate that same thing in you, by asking you questions. Hey, does everybody follow here? What's you know things of that sort, just to get you kind of pulled up and active. That's going to kick up some of those beta and gamma waves as you're pulled into the a little bit more of a discussion. Um, we're not a huge number seen here, right? There's 6 of us online, so it's not bad for discussion purposes. But anyway, that if you do that, it'll help you to remember more the more you can tie in. All right, I'm gonna try to share my screen. Let me see if I can find MATLAB. So hopefully everybody can see MATLAB now. Um, all right. So some things here. I've kind of got my a general MATLAB folder. I throw in all the stuff I kind of want to add and things I write for different classes. I just kind of dump in this MATLAB folder so I can find it easier. I'm going to use EEG Lab. So I have this tendency not to delete old versions because they're just a bunch of scripts. This actually isn't even the most recent. There's an update I should have really probably pulled in, but it never caused me a problem, so I've never bothered. Um, but when you add EEG to the path, I've already done mine, but I just want to show you here briefly. So when you get the add to the path, you have there's normally two choices there here. One is to add the folder, selected folder, and then there's this one that says selected folder and subfolders. For EEG Lab, you have to do the one that says selected folder, not the one that is selected folder and subfolder. If you do both folders and subfolders, they use their subfolders to kind of separate out different functions that sometimes have this, same or very similar names. So they don't like you to add all the subfolders because then MATLAB will search through all the folders and find it themselves. They like you to go to the top level folder and then they can use explicit paths to pick out the one that they want. This becomes more crucial when it has the ability to kind of load in its own little functions. So if you've added the subfolders to it, then if you load in other functions, it's really easy to get name collisions. So generally recommended that you do not add those subfolders. To launch EEG Lab, you just type EEG Lab. Right, so just like MATLAB is a matrix laboratory, right? Things of this sort. Um, so, this is following that same idea, right? Electroencephalography encephalography lab. We'll type EE lab. It'll launch some stuff. It'll tell me, by the way, you should upload the new versions. And I say, thank you very much. Um, I'm gonna make this a little bigger because I've noticed every time it launches for me, it doesn't the text doesn't fit full size. So if you're trying to follow along and do this, um, the EEG lab is just a bunch of scripts. So you don't actually have to have it um, set up as a independent thing. There's no fancy thing. You just download it, dump the folder where you want, add to the path, and you're off and running. I'm going to stick to just basic functionality here, so you don't need anything heavier than that. All right. So far, so good for everybody. Um, so
Yes.
I'll give one added thing. When I go sharing my screen, this is kind of a WebEx weirdness. I don't get to see the chat window anymore. Um, it's kind of an annoying feature. So unfortunately, when we do get for me asking questions and interacting, you will have to turn your mic on to interact. Um, if I had a nice way to do it, I would, but unfortunately, for it to allow me to see the app and you to see the app, it's kind of got to remove a lot of the other windows to them. All right. Just out of curiosity, is anybody also following along in their own version? It's optional, but
I was trying to, but then MATLAB decided to close.
um, I'll give you a sec to launch out. Did it say what your problem was?
I'm betting it did, but I just clicked OK.
Ah, try to relaunch it. It shouldn't take too long. It is really helpful. I find that, when I first started using it, or any other type of tool too in MATLAB, this is pretty generic. Um, when I listen to it, it always makes sense when the person says. When I click it myself, I kind of have to force it. Um, my brain processes different when I'm doing it. So when we go through and do this, the first thing you'll have to do when you pick them here is we need to get a data set. There's a couple different ways that you can get data sets. The most basic one, we're not going to do it this way, is to actually import the data. Um, so there are kind of different standard interfaces that are used, um, including some plugins that you can measure from so different companies. When you do these measurements, um, they will output their own files, like Neuroscan has their EEG file. There are some standard ASCII files. Like different ones have uh, different kind of standard file formats. So when you're measuring an EEG, it'll automatically store it using these kind of standard formats. And so you can just import the data from these standard machines. Um, there are some standard data formats. You can also kind of add your own into their definition. In our case, we're going to load an existing data set. So, um, the data sets are if you've already imported data and you've done, well, technically you don't have to do anything. You just import the data and then you could save a data set that's been loaded and it loads it into EEG Labs kind of format. And their format is designed to make it easy for their functionality where you can, do the various event loadings, which are held differently. So you can see import event data and epoch data, um, things of that sort. So the load existing data set means it's already gone through that data load process. They provide us with 3 data sets as their standard. Um, EEG lab data is the one they provided for a long, long time. EEG data 2 is a newer one they've put. Only in the more recent versions that are on here. I think this one has some noise in that. I've usually just used this first one because it's a pretty good example. And it has a virtue of being small. It's got they lowered the sampling rate for us and things of that sort. We'll talk about that in a sec. But this one is usually small enough that it doesn't kill you when you have to do processing. For an awful lot of these, they can be measured at um, you know 256 hertz or even sometimes a kilohertz. That's on, believe it or not, the little headset I was using actually is measuring at a kilohertz, a very fast signal. So when you get any decent amount of run, like let's say you were doing a larger study, which, maybe takes, you know, 15, 20 minutes, maybe even, an hour or so. If you're measuring at, every millisecond, you're going to get a lot of data. And it's not uncommon to have, 64 or more channels in a large data set. So this is just a huge amount of data. When you go do ICA on this, you know, you can you can seriously have your computer sit there for an hour or more trying to process all this data. So this one is nice in that it's will run and not kill my machine. Um, so I load in that the base data set, and it's going to tell me how many channels do I have. I've got 32 channels, right? Basically, it makes one big epoch. Epochs are kind of like big time periods, and it tells me how many frames each of these individual measurements across them does it use. So that's kind of my total measurements. It'll tell you when the epoch starts and ends. It's sampled at 128 hertz, um, which is you really don't want to go smaller than that. That means 64 hertz is basically the highest frequency I can measure. Remember, so this is sampling frequency, and Nyquist tells you you can only get up to half of that for actual legit data. So that gets me a 64. And remember, high end of gamma is, well, people can, it kind of argued, dead minimum for the high end of gamma is say 40, 45. It can go up to 100. So at 64, I really can't go lower than that and get anything decent. If I were to try to cut the sampling rate down to like 64, I'd only be measuring 32. Um, I'd I'd barely have any of gamma at all. Now, if you're only interested in going up to beta, then that's probably fine. But realistically, 128 is about as small as we would ever want this. When you're measuring, you usually measure higher. Um, but in this one, they had a higher sampled one and they downsampled it. Um, Downsampling is commonly done to make it a decent amount of processing. And you can see even with a 128 in a second, they've got, was it 4 minutes? worth of data basically. So you can see there's an awful lot of frames they're dealing with each channel. Now, um, for reference right now, it says unknown channel locations. No, it doesn't. ICA waits, not yet. So we need to go through and we need to handle each of these different ones. I'm going to do the channel locations first, and then we'll talk about some other stuff. Actually, maybe the first thing I should do before I even do channel locations will often come in when you first load it. It's a good idea to kind of take a look at your data. So I'm going to go under plot and just plot the channel data. Um, and you just want to check and see of, oh, does this have what we want on here? Now, I mentioned that you sometimes have to come in here and you might have to um, import event info that's on. But if you notice here, I already have event info that's available. And it says events 154. Now there's two types of events in this data. This is a pretty simple, if I make this bigger, it's easier to read. Can you actually read what these say?
Definitely not.
Okay.
Yeah, it's
Um,
small on that screen, but I pulled it up on.
oh, you've got your own running?
Yeah.
Awesome. So yeah, I'll be honest with you. I can't actually read them either. I just happen to know this data set. So I know one is square and the other is the response time. So this is a study that was done, and it's a fairly typical one where they have a screen that's up and they'll show a square will appear in different areas on the screen. Okay, a text thing popped up briefly that said somebody's asking for where do I load stuff. So if you're trying to load the data set, go to File and Load Data Set. And um, I'm in sample data, which is inside EEG Lab. So mine just opened up there, but you know,
Where do you get the blue file, the EEG lab?
um, so EEG Lab is not built into MATLAB. Um, EEG Lab, you have to actually, if you go to pick up your favorite browser and go to your favorite search engine, whatever, Google or whatever makes you happy, and type EEG Lab and then maybe download. It's supplied by UC San Diego. They're the ones who developed it, and they have a free download. So I have a link
I
for
just
this.
pasted a link to it.
Awesome in the chat. Yeah, I think I had mentioned all this in
Sorry about
the
that.
yeah, no worries. But if you need to find it later, um, it's on there. They'll you have to go there. They'll ask you for like your name and an email and stuff. They do that because they have it's totally free and they don't care negatively that you're using it. They're trying to build up their user database. They get development funds from federal grants to keep developing this. The more people that use it, um, basically the more they can say to the federal government, hey, look, lots of people want this. So they keep a list because it helps them try to compete for grants and things like that. Plus, they also have a conference they run. Used to be every year, but maybe the last 10 years it's been so popular they've been running like a European and a North American and I think an Asian um, conference. So like three of these a year. Anyway, you can download that and then pick the EEG lab data set. All right, and then plot channel data, and here you go. So anyway, the idea of this is they pop up a square in different areas, and then the person has like a button to push or something of that sort. And so they'll say, here was the stimulus, and here's the response. right? And so RT should be what's there. I just see a couple little squiggly lines. Sorry. Well, as years go on, my eyes get worse. But usually RT is the symbol. It's small enough to be that for response time. They can measure from when the square appeared on the screen to when the person was able to respond to it. And you can see that there's some characteristic activity, and they're trying to look at this and see, okay, what's the stuff that's handling the visual processing, the recognition, and then the motor planning to say, boom, go. Um, so, motor planning, depending on whether the person was using left hand or right hand to push the button, right? Your right hand motor planning basically is in this area of your brain. For the left hand, it's usually here. So we should expect to see something go in here as an activity for that. Most of your visual processing is on the back part of your brain. So we should see something here and then, some activities for the motor ones going on in between here. Now, from all of these channels, we'll have to find out where they're located and things like that. You'll notice these channels are just numbered, no fancy thing to them. So when we go to localization, we're going to have to um, rely upon them supplying us a map. If these channels had more intelligent names to them other than just numbers, then we could kind of use a standard mapping. So we can see kind of all these. We see some weird artifacts that are also in here. All right, we see these kind of jump dot discontinuities that go on. Um, if you ever get a data set and it looks like completely blank, like you load it up and there's, maybe there's event markers, but there might be one or two traces and then kind of like a whole bunch of nothing. Um, you know, if that's the case, that's often happens that if there's like a baseline, a DC offset, the DC offset could be so big that it's not on the screen. Right, so you've seen this inside EMGs and everything else. So you might have to just remove that baseline from them, and we'll talk about removing baselines. But we can look at this and kind of, um, our data. This is not a particularly huge data set that's in. Um, sorry, I was scroll over a little bit. You can select things like right here. I see that discontinuity. I can mark it. You can use this to reject. If you reject, it literally deletes it. So be very careful when you're doing that because you want to make sure it's real things that you're deleting. Um, One thing you'll notice in here, these lines are very smooth. There's not a lot of noise. This is an extremely clean study. I would imagine somebody has already kind of pre-processed this. Now we'll take a look at a few of these things, like right here. There doesn't seem to be as much action on, um, both was this 15 and 24 as channels. Um, I'd be willing to bet, just given the look of those, that those are probably right just above the ear. Um, those tend to be very noisy channels, and if they hit it with a filter, you it tends to kind of flatten them like that. Um, they tend to be noisy because a lot of like if you move your mouth, right, that muscle connects up here. There's just a lot of muscle activity connect to this area. So, wiggling the ears, all kinds of this type of facial action, we'll usually get a measurement in those areas. They tend to be fairly noisy. And so they're often right above the ears, right next to the ears, are also used as a way to remove muscle activity on the brain from these different ones. So, but it looks like somebody's already cleaned these channels. When you see muscle activity, it's like a lot of high frequency noise. So it'll look like a really thick line when a muscle activity goes in. Um, but I'm not seeing a lot of muscle activity in this. So, that tends to indicate that somebody's already cleaned up the data pretty nicely. The other thing I'm doing is I'm looking, usually your eye channels tend to be towards the top of this. Not guaranteed, but usually people start numbering in the front and move back. So I'd presume one of these is pretty close to where the eye is. Um, and so, the eye channels usually tend to have strong blink artifacts, um, and those ones are kind of fun stuff to remove. I haven't used this data set in 2 years, so I don't remember if the blink artifacts have been removed from it or not. It's pretty smooth. Usually blink artifacts tend to be bigger bumps. Um, you can see a little bit of a discontinuity here, which tells us there's some things to move up. And you can again see, right, these, here's my stimulus and here's my response. And you can see some very characteristic waves that are going in. But like these discontinuities, we might want to try to clean up things of that sort. You can see another big discontinuity. These happen. It doesn't, sometimes the person kind of wiggles and the electrodes don't connect right. And if, or the person sneezes or something, right, you might get some type of, this is a very clean discontinuity. Sneeze, you tend to get like a lot of muscle stuff. Um, but somebody might have come in and also cut that data out. And so now they're spliced together. Another reason those sometimes happen. Um, it is possible that some of this activity could be cleaned up, things after a muscle area, right? There's a stimulus, a response, and people right after they do some response, they'll often like their eyes will move or they'll kind of stretch their face or something. So this could be the result of just some muscle activity in response to this. So usually you want to just take a scroll through. This is kind of very typical brain looking activity in here. Um, yeah, see, you'll see this. This is very characteristic of a blink. Right? So you can see this big old spike coming off. So these probably are the eye ones. This one's in the negative direction, but again, remember that's not a big deal. It's just measuring, right? If your electrode to its reference is reversed. Um, so there's at least one big activity that's removed. Um, Generally, the best way to remove blinks is not to try to filter them. It's to let ICA separate out a blink channel, and then you delete that channel. And so we're kind of looking through for those. We do see a little bit of a disconnection here. Um, that could cause some of this spiking that's going on. You know, some area there might be some eye movement that was happening, maybe for this particular one. um, the square might have been in a different corner of the screen, so the person's eye had to drift or something. But this is actually really clean, honestly, looking at this data. I forgot how clean this was. There's not a lot of drift. There are some discontinuities, but you can see a little more as we get further in. A few other discontinuities and artifacts. I'm surprised. Okay, you can see now this is some big blink, and I, maybe they scrunched their nose or something. This is a lot of things happening in the front part. I would imagine this is probably mostly prefrontal and frontal part. You know, um, I said this is probably in the temporals right above the ear, like maybe uh, T8 and T7 or something. Anyway, I don't see any other kind of interesting features. I was hoping we might have some dense squiggles that indicates muscle activity. Um, Usually, it's much higher frequency type of a noise, but it's significantly high, so it looks like very thick things. And then eye blink, it looks like happens uh, in the middle of it, like the square happens and the person's eye blinked involuntarily as a result of that. discontinuities. I don't see any major, not a lot of cool features. This is a pretty clean data set. You can see some more discontinuities, some more probable eye blinkage. So these first couple channels are probably the eye measurements. All right, so that gives us an idea of what's going on with these. We can see the event types. Um, so once we've got that, right, we've got our study loaded and everything. If I was going to, have to attach on information about the locations and that, um, you can infer them, or in our case, we can also, there's a channel locations here that comes in, and so you can kind of from these. So if you go to edit and channel locations, that's where I went for those of you following along. Um, so there are different models that are on here. Ours doesn't have that type of data. They're saying where do you look for them. Um, so we're not going to do anything with this. Cancel and OK should do the same exact thing. It should pull up the yeah, it does. So when it tries to infer things, it just pulls in one channel because it doesn't know what to do. So we're going to go down. If you see this kind of just above help, there's this read locations. They provided us a data file that goes along with this. So under MATLAB, so I'm in EEG lab 1411B. And then under sample data, there is also sample locations, but I believe they stored for this data set, I believe they stored the locations. Yeah, here it is. It's under the data one, EEG lab channel 32 locations. So this is the data file that goes along with a data set. So I'm going to open that up. So it's going to ask you, hey, do you know what file it is, or do you want me to try to figure it out? And I'm going to say, yep, you figure it out. And so now it's got all of our information. So, like the prefrontal 0, right, dead center. So we can start getting, some of these type of measurements on here. We can, do a lot of things. We can look up the data. We can plot these in 2D if we want. It'll show us where our information. So it does turn out electro-optogram 1 and 2. So there are 2 eye channels, which is what I kind of thought. There is that prefrontal 0 that we had mentioned, frontal 0. So you can see the Z's running down the center. And they do have, yeah, I was saying that it might be temporal lobe 7 and 8, and it is. That's probably the ones that was whatever 15 and 23 or whatever that was. And you can see for each of these, right? So there's the prefrontal, the frontal central, which is between these two. The original 1020 system just has kind of the main ones. And then as they added more detail, right, they added a row in between the central and the parietal, and it was called CP, and between the frontal and the central, and that's called FC. You can see the occipitals in the back, temporals kind of along the sides. So it gives you an idea of these. These electro-optogram channels will also work to kind of pull out a lot of facial or eye ones. I don't know why they're sticking them off the edge. They really should be kind of just right there and there, but they do actually physically locate them on the map as an idea, because this is where it's going to plot kind of that brain activity for us. So, but it's kind of nice to be able to see, so you can look up the locations and then plot them in 2D, and you go, oh, okay, I can see where my channels are. You got an idea of what the measurement is on here. So I say, okay. And you can see now the channel locations, it said yes, where it said no before. you know, we can find out. I'm not sure if they tell us any more about this, but the about the data set under edit, you know, so they do different. So there's 5 different types of squares. Central fixation cross, and the person has to different colors. Okay, and if they're, yeah, okay, and there's circular disc, and they have to ignore it. So you can kind of read this and see what they were dealing with, for the different events and why they were labeled. So we're going to go now to the tools area. So one of the things we'll often do if you're dealing with a decent amount of data is you might have to change the sampling rate just to get small enough so your system can process in a different decent time period. Right. Ours is right now 128. Like I said, you don't want to go smaller than this. But, you know, let's say, for instance, that this was at 256. I could then type 128 to cut it in half. A little different. It's not just going to, um, when it calculates those, it's going to calculate that at the lower rate, but then it's going to apply a low pass filter at half whatever your sampling rate is. Because remember, Nyquist says, for instance, here at 128, means 64 hertz is the highest frequency it will measure. So um, if this had been something higher and I was going to 128, it will resample to 128, and then it'll apply a low pass filter with a corner frequency of 64 to remove any of those other harmonics, and it just gives you a cleaner data set. I'm going to say cancel, but if you had a ridiculous amount of data, way too high of a sampling thing beyond the range, and remember, your concern is to go to the smallest data set that's going to carry all the features you want. So 128 is reasonable because you can get to 64. Um, you know, I can filter the data. I would not filter the data as my first action. There's kind of almost a natural tendency to go through these. But I'm going to suggest one of the first things you're going to want to do after, if you had to change the sampling rate, I would do that first. But then remove the baseline, right? Once you've set your sampling rate, I personally recommend to remove the baseline. Now, the way that the baseline works, right? It's going to actually just calculate the mean for each channel and remove that. Now, that in theory is pretty similar to what you get if you pass it through a high pass filter. However, it's not exactly identical. This works actually a little bit better to just remove the mean if all you're trying to do is remove the DC component, which we usually want to. We typically don't care what the DC component is because it's just easy to get that wrong. So I'm going to remove the mean of my data. Mine was pretty good to begin with, but it's a good idea to remove that mean. And you can do that whenever you want. It's a very simple action. You're not going to screw up your data. It's just a DC offset to keep things in. ICA does not tend to like having a baseline in there. It should remove it automatically, but since ICA is our goal, that's a big thing. Then we're going to go, after we've removed the baseline, we're going to go and we're going to filter our data. Now, they give you a bunch of different options for them. I'm only going to use the new version of the FIR filter. And we've already done a bunch of FIR filters. FIR filters have the good features and bad features. But one of the nicer features about it, it is pretty linear. In our case, the like linear filters also will tell you though that you're going to get a phase shift. But in our case, for analysis, we're not going to get any phase shift at all. That might sound like a weird comment on my part, but the reason you get the phase shift is typically you're doing this type of processing as you're measuring it, which means you can only apply the filter in the forward direction. So the phase shift is going one way. If we don't filter, we just collect all the data and then we apply the filter later. What they do when they apply the filter is they apply it in one direction and they also apply it backwards in time. Right? And then they combine them. So the net result of doing both is that the phase shift from the going one direction in time versus the other direction in time cancel each other out. So you end up getting no phase shift as a result of it. Now, when you're doing, particularly going for an ICA calculation, we've got to make sure we clean things up quite a bit for them. So we've got the lower edge of the frequency band. So for ICA purposes, 0.5 hertz is a pretty good lower edge. Depending on the analysis you're doing, ICA I wouldn't go less than 0.5. Maybe 1.5 is pretty reasonable though, but definitely don't go below 0.5 if you're doing ICA. There are some analyses that you will actually want some of these, lower frequencies, maybe going down as small as 0.1, but, um, the drift that results, right? Because these are very slow waves, right? And that kind of slow oscillation really will throw off ICA. It's going to see that as a signal, and it's really not. If you do need those for other analyses, it's almost reasonable to do separate ones for the ICA part and to do the other, and then just take both results and combine them. I'm not going to worry about the higher edge. Since it's 128, I guarantee they did that from something else. So it's already been hit with a low pass filter at 64. So I'm not going to sweat the high end of this. They do have options for notch filtering and things like that. I'm going to leave this plot frequency response on so we can take a look at it after we've done this. So it'll show me. This shows you what the response is, magnitude and phase. Now this is very small, so it looks like it's dead on. If we were to zoom in, you should see, I zoom right in up here. You can actually see that response here. And it drops off right after that 0.5. If I zoomed in more, it'll be down a little bit there. But that's kind of my central spot. You can see it's a very linear phase, but again, we're not going to worry about that. We go, yay, that's fine. Now you'll notice every time I do any major thing, it's going to ask me, do I want to give this a new name? Do I want to save it to a new file? Since some of these operations, particularly for big data sets, are really darn slow, and you might want to come back to it, I might not want to have to redo this all the time. And you have the option to overwrite in memory. So I am going to overwrite it in memory. Usually if you were doing this for like a real data set, I wouldn't, unless my computer had very limited memory. But I'm going to do it. You can have multiple data sets that are kind of loaded. I don't want to have confusion when you're going through here. It would be reasonable to save this and to keep the different versions so you can go back if you make a mistake. In our case, we haven't done an awful lot, so I'm not going to sweat this. It will ask you this all the time because when it deletes something from memory, it really deletes it. So the only way to get it back is to reload from one of the saved files. I'm going to go ahead. We've now got even more cleaned data. Let's see. So we have now removed our baseline. We filtered our data. I'm going to come in here and take a look at re-reference. you'll notice it tells us right now the reference is unknown. And there's a few options you have available to you. So we can compute an average reference. We can re-reference to a particular channel if we want to use a particular channel. We can also exclude channels like EOG and things of this sort from them. Now, if we click the list, it'll show us our particular EOG channels. So often, only control lets me do this. I'm just going to remember my notes. What is it? 2 and 6. So the reason why we would want to exclude channels, and they suggest like EOG and EMG, the electro-optogram and the electromyographies are used to measure either muscle activity or eye activity, which is again heavy muscle based. We might not want that in an average. So what they're doing for an average is you can essentially assume the neck is a pretty good insulator from the rest of the body. So all the electroactivity is really going to be coming from the head. If we assume that you've been, kind of just doing normal thinking, no strange things are happening to cause electrical fields to build up. The average across the person's head should be a pretty good measure of kind of the quiescent or middle state of to reference off for brainwave activity. Um, it is a pretty good assumption. It generally works well. The only time these averages don't work well, if you've got like a heavy cluster, like maybe I'm just measuring heavily prefrontal or maybe prefrontal and frontal types of areas, then it is possible that that average might not be so good, right? So if I've got some sparse ones in the back, but really dense in the front or whatever, the average might not be a good reference. We generally do not want the muscle measurements going into a central value for calculating brainwave activity relative to that. But in our case, they were spread pretty evenly. I don't want to have the EOGs, which is a muscle thing inside there. I could alternate to this. I could actually say to reference it to a particular channel. If there's one channel and I want to see how the other ones look relative to it, that might be a reasonable way to go. And you have the option, you can retain that old data, but realize if everything's referenced to there, then essentially that would go to 0. We can also calculate this backwards, the reference channel back into the data. So when I go to compute the average, if there was already one that was being used as a channel for reference, that means it technically is gone from the data, but I can get it actually back because every single one of the channels has it subtracted from it. So when I calculate the average, that technically has this channel's information into it, and I can therefore subtract it out and get it back. They ask, do you want me to do that? At the moment, I'm not referenced to anything, so there's no reason to do that. So I'm going to say, yeah, just compute the average so I have a known reference point, and don't count those. Right? Now, by re-referencing the data again, they're like, hey, you want to save this, right? Again, if this was a big file and this was taking more than a second or two, I'd say yes. I'm just going to overwrite it because there's no real need to in this area. Okay, and now you notice my reference now tells me that I'm being referenced to the average across. Might be a good idea at this point to kind of, let's take a look at our channel data. We can see it still reads pretty clear. You'll notice instead numbers now we are able to see some particulars, and notice how there's this kind of higher frequency that's coming in here, particularly on my EOG channels. Right, so a little more muscle activity going on those. You can see it now that I've calculated the rest. This is relative to brain activity. So you can see all the EMG, instead of being spread to the rest of them, are kind of concentrated. So again, I could look through and find, and if I found a bad area where the data was like really ugly, there just isn't a lot of ugly on this. But if there was an area that I was looking at and I was like, ooh, this is horrible, probably a blink right there. Maybe if I wanted to get rid of this, I go, oh, this is a horrible discontinuity. I just click, drag, click again, and I can hit reject and it'll just delete that period. I'm not seeing anything major here. So when in doubt, um, there's kind of an old joke in this. When in doubt, you're not in doubt. So what we're talking about with that type of phrase is when in doubt means if you're wondering, should I delete this or not? If you're wondering if you should delete it, you shouldn't be in wonder about deleting it. That means you really should keep it. You only remove stuff if you look at it and you're like, I am sure there is something wrong with this. So the only reason for deleting something is because you're positive you should delete it. I'm pretty happy with all of those right now. So we've now re-referenced. I could interpolate electrodes if I wanted to get things in between, or to re-add stuff in. Do not ever interpolate electrodes if you're going to do run ICA. It'll really screw with stuff. This reject continuous data by eye. So if you were looking at this and it was a messy data, you as a person can go, and we're actually pretty good at doing this type of stuff. And they'll tell you, give you some information, mark the regions and everything else. And I'm going to show you something kind of cool. When you do this, it should look familiar. Right? This tool, reject by eye, take a look at that one. Boom. We go back to plot channel data. Notice the similarity? I hope so. It's the same thing. Right? So plot channel data is identical to project continuous data by eye. I believe they just put it in here just to, in case you didn't know, that was where they did it to allow you to have them. Extract epochs is, like I told you, by default you get one. But like, let's say, for instance, there were sequences of your data test. Maybe you're going to initially do a section of testing where the person has to just notice squares appearing in different areas. And then you want them to do in a second section, you show red squares versus blue squares or something. And you want them to do something different. So now they not only have to find the area, but whatever. So you're asking different types of questions. You might want to separate those into different epochs if you were doing different types of tests or things of that sort. But anyway, we're looking pretty good on these. Another one that we'll want to do is sometimes take a look, in addition to the channel data, channel spectra and maps. So when it lists these areas and you pick channel spectra and maps, it says epoch range time. So it's from 0. See that little space? That really is a separator, and this is to whatever the full 238, seconds and whatever. So you get a huge thing. This is in milliseconds. So remember, of course, you got to take the thousandths off. So 238 seconds. So this is your full data run. Percent of data to sample. They give you 15% as a default because data sets are usually large. Ours isn't, so I'm going to show all the data that's in. Um, so frequencies to plot. I'm going to let the whole thing go. Plotting frequency range. I'll just leave their choices. We might go a little higher than that if we want this array just gain through beta and that. But so what this is going to do, it's going to plot our data for it. So each one of these is a different channel, and it basically superimposes them. Now there's several things that we often want to look at on these charts. That's happening. It'll give you a rough area of what type of a map we're going to get at different regions, right? And so some key frequency things. So you'll see right here, this is right around 10 hertz, we see a spike. So there's an alpha wave spike that's happening. And as a general rule, remember I was saying you're going to see this kind of decaying curve. You can definitely see that kind of decaying curve with a spike in the alpha wave zone. And you can see the alpha wave zone happening right when this spike goes on. You see a spike in the back and you see a spike in the front of the head. The back of the head is where you do your optical processing, and the front is going to cover your basic eye motion. You're going to get a little thing as the person's eye focuses. So this is probably the eye actually focusing more from EMG type stuff or EOG type stuff. And then on the back here, this is actually processing the image in the occipital area. So fairly intense on that. The response, when you get to this area here and here, these are the areas of the brain that are typically associated with trying to do muscle planning. So somewhere right around there. So there is kind of an intense peaks. That might be it. It's hard to get the exact measurements off these heads. They were already kind of shifted a little bit. That's a little too far back. So it's kind of like right here. So right about where those dark reds are is about where your muscle planning is. So when you have to do the reaction time to give the response, this is probably doing the what should I do? And that's happening in that, mid to high beta range, like we said, right? Somewhere around 22, 23 hertz. Yeah, 22 hertz. We're getting a response here where the channels are measuring, this person is thinking about how to actually press that button, right? So they're noticing the thing and they're causing the response. So you can actually see the two main activities that's going on here. You know, this one heavily right in the front, that's probably just purely muscle activity and action going on. So not too big of a deal. The reason why we show these is we kind of see, oh, does it look reasonable? We're looking for that reasonable intuition. Okay, alpha waves handling that, where it goes. The planning being more in the beta wave zone. Okay, that again makes sense. We do see a little bit of outliers. These two here, the red and the blue. That's another thing we can do. And you can click. When I click on this, it says channel 1. Go down to the blue and click on it. It says channel 17. So it's telling me 1 and 17 are kind of the extremes on these two. And that allows me to then go, oh, maybe I want to look at those and see. When you see a bunch of them kind of clustered together, that means they're pretty consistent. And so, that's kind of more reasonable activity to us. I can click on some of these other ones here and see, okay, channel 6. There's another one there, but zoom in more to,
Dr. Schubert,
yeah.
we're trying to, I mean, I try to do the same thing, but it tells me to run ICA first under tools, but I don't have that option.
So to generate these maps, so it could be generated by ICA. They can also approximate this from some other means. On mine, it's just doing an approximation. It is possible to get these map pictures that they're having to do a full ICA on the version you have. I have an older one. This is not a perfect map. They're approximation maps that's on. So they're not doing a full ICA. They're just kind of doing a quick and dirty approximation. So they might have changed that. Like I said, I have a slightly older one. I've downloaded and used this one for like about 5 years.
I figured out I did it wrong. It's all working now. Sorry about that.
Yeah, no, it might actually not be you. It might be they've changed on the newer ones. Like these, like I said, they are quick and dirty, so they're not that accurate. That's why I'm like, it basically is in that area where I would expect muscle planning. But I don't trust their map completely. That there's activity somewhere in this zone, yes. How precisely it's cutting, not so sure about that one, right? That there's something going on in the prefrontal and the occipital, I'm pretty sure, but the exact area, I mean, it looks on this one like it's a little bit, maybe that's center, maybe a little bit further over. You know, so you often get recognition on this part, when you're trying to classify stuff. So it is possible that there's a little bit wider towards that classification area. And I think they had said they had a couple different types of squares. I mean, it sounds reasonable, but with this being a down and dirty approximation, since we haven't done ICA yet, I wouldn't be completely certain. But I usually like to do ICA as late as I can because ICA is slow. And if we were in here and we saw a channel that was like way up and out away from the rest, or if it's behaving weirdly, this kind of downward trend that you see, kind of the 1/X shape, maybe with a couple lumps, perfectly reasonable. If you see it where it comes down and it goes back up again and then levels off, so it kind of goes and it goes up and levels, that's very characteristic of an EMG. So if it was kind of higher through this frequency range, a dip down and then up at the low, right? Doing that type of a shape. I would tend to think that's more of a muscle response. You'll get that heavily, particularly at the back of the neck. Ones will have EMG noise. Sometimes if there's ones just on the front of the face and the person like squints their eyes or something, you'll get a heavy EMG response. So if you see that kind of down, back up again response, then anticipate that it's probably an EMG. And then we can click on it and it'll tell you the channel here. And then you can go look at that channel and see, is that reasonable data? That's actually a good question on your part. So don't think that's wrong. I'm sorry. It's evidently the new version doesn't give you this pre-guess. And it's really just helpful to avoid time problems. As computers are getting faster, they might also be assuming that you don't need it as much. All right, so we've kind of gone through everything we need. The only thing left is actually to do the ICA itself. We've got everything cleaned up. We could remove components if there was something bad. We've identified channels. I'll just show you. Okay, on mine, they're even making me do ICA first. ICA is the best way to remove components. So they give you a bunch of different options of calculating ICA to use. I'm going to use Run ICA. It's a pretty standard one, and it says, I can pick different channel types that are in here that I want to run for them, but I'm not going to worry about that. We're at our time, so you can see just like you did before, it's going to use because Run ICA tends to use Fast ICA as their algorithm, so you can see it's doing all the different steps and calculating them. The mixing matrix W that it's trying to find will give you the maps of the head that we were showing. It'll do it more accurately, but it's don't ever take it as complete gospel truth. ICA is not perfect. Right? And we showed you this. We can tweak things and whatever. So there will be some errors that go on in the data when you process them. If this was a huge data set, I'd say, hey, let's go talk tomorrow. I'm hoping this will be done fairly quickly though, because this is a fairly small data set. But when you're running your own, you never know. Once this is done, you'll have all the ICA weights, and then you'll be able to plot a lot of these extra modes. Hey, so it did finish. So you should be, once you've run ICA, you can go now reject the components from ICA is one final important thing just to mention. I'm going to plot all 32 of them. So it's going to show you all of these when they go in. When you're plotting by component, so these are the weighting matrices. That's going on. If I see ones that are just single components, you become a little more suspicious of them. Way down in the 30s, this is your biggest component going down to your smallest component by how much it affects it. A single component is suspicious, but way down in the 30s, who really cares? It's down almost to the noise. This when you see a big thing in the back, this is definitely processing your the images that it's noticing. This is probably blink, just given it's right in the center. A single one right in that prefrontal cortex. So this is probably actually the blink response on somebody. This, like I said, is probably hitting a lot of the muscle planning areas. Recognition and classification ones happening on either side here. This one, a little, I am kind of questioning on that one too. But we can take a look at each one of these, right? So this one I'm going to bet 3 we can say is, now if you were to pick this, if you double click it, you can see the power spectrum dropping off. So that is actually a reasonable drop off for them. It is kind of sporadic. So they will list out, all of your, usually it does time this way. And usually when you see these little kind of hot spots scattered, that is very characteristic of blinking. Usually you'll get kind of like a whole wide band that will come across if it's a normal situation. I'm willing to bet that's a blink, but I can't tell exactly for the moment. They sometimes give you a graph in here of time, which is helpful. But at the moment, I'm going to just okay this. Sorry, accept my. So you have your choice of accept or reject for them. If you reject, it doesn't reject yet. It'll just mark it for reject. And then if you hit OK, then it'll reject it. So you can look through these. Normally you find ones that have just a single active node that's dominating, kind of like this one, or that one looks like a single. This one, that one might be. And you just check them out. Don't just reject automatically. So by default, you're suspicious, you look more into it. So I kind of find my judgment calls on there, and then I can come back and take a look. They do have some automated ones that will kind of do some guesses for you. So if you want to look at them in more detail, the channel spectra and maps will help you on that. Then you can come back in, plot all the data. I'm gonna let this go up a little higher. I plotted it a little higher because you can see right here, right at 60 hertz. So you can see that's where their power came in. So, you know, this data set was collected in the United States. You can just tell because it's 60 hertz. Mostly in Europe, you'll get closer to the 50 hertz zone. You should, after you run the ICA weights, you should be able to see the data for these. But you could then plot them, and you could take a look at each individual one, right? So the frequency versus the decibels. But you can then look at those channels and decide what do you want to do with them for each one. So that gives you an idea of how you can kind of show and take a look at some of your maps for each one of these. I'll do one final one, the component spectra and maps. I'll just take their defaults. We're only going up to 25 on here. So, you'll see it's the same type of a one, but now I'm doing it for the individual components as opposed to the channels. So the components are what you get out of your the ICA. So as a result of it, now I can look at the individual components from ICA and see where do they fit on the curve? Do they kind of fit the same thing? So I can see that, my channels, oh, that, or sorry, this particular component that's here, what does it get? And so it's drawing the lines to the individual one. So this is a really strong one. And I can see its peak here at 10 hertz in that alpha zone. Um, you know, that allows me to kind of tell what type of brain activity is happening and where it's going and look at the channel separate from each other, right? So this one's activity here, and I can click on it and pull it up. I can see that back area, which is often associated, like I said, with kind of class, like recognizing faces and stuff is often back in this zone, right? So recognizing faces, shapes, it's kind of reasonable that that would be there. And you can see it's a pretty dominant mode. It's one of the upper ones. That's why they connect them to the lines to let you know which one it is. But that gives you the idea how you can look at them and analyze them. We're out of time, unfortunately, but I hope this gives you a good sense of how you can use. It's a really nice, powerful free one. You really should go through that time to pre-analyze before the ICA, because if you do any of that other analysis afterwards, you have to rerun ICA. And then once we have the ICA, I can then have these components which let me see, oh, what's the actual activity in this kind of brain mode that's happening? And now that I know where it's happening, I can say, oh, wow, there's, a lot of alpha wave in the classification area happening when the person's trying to determine the square, things of that sort. Do we feel good? Do we have any questions?
Yeah, I was wondering if Tuesday's class would be recorded.
If the upcoming Tuesday's class or the last Tuesday?
This past Tuesday.
It should be. When I checked it yesterday, I didn't have, it wasn't ready yet. I'll check again. You should be able to, if you go under WebEx, and I don't know if I can. I'm gonna stop sharing MATLAB for a sec and see if I can share. Maybe I could share my. No, it's okay. So I'm kind of sharing my screen. If you look under, so this is the WebEx interface. Like usually you're here under event calendar, and that's where you kind of launch your areas. If you go to event recordings, so this is today. Okay, So you can see Tuesday, it's actually finished now. So now it says view recording. So if I click on view recording, it'll pop this up. And then I have a streaming option or a download option. So it is ready now. It wasn't when I checked yesterday. So I'll download this one, then upload it back up again. So you know that I'm doing it. I'll click it now. Hopefully that won't interfere with our areas. But you can also just stream it yourself. Download isn't usually too bad for me. Upload is slow because upload speeds are always slower. But I should be able to download this and have it up, and so now it's download. Probably take me about 20-30 minutes to get uploaded, and then once that's done, it'll take a few minutes to process inside there. The software inside, because unfortunately I can't use WebEx's event recordings. I can't just pull them inside, as dumb as this sounds. I can't just load it into the My Media area. So I have to literally download it and then re-upload it into my media gallery to then share it with the rest of you. So
Okay, I see it now.
as
Thanks.
soon as that's done, it'll be good. But you can always look at it on your own too. Any other questions? Well, awesome. Have a good day.
You too. Thank you.